Good afternoon, everyone. So, we have started the unit on neural networks, and last time we were discussing some rules for training a neural network. So, we looked at Hebbian, we looked at perceptron in the last lecture. So, perceptron, along with the role of the bias, was what we covered as part of the last lecture, and we solved a problem based on the same. Also, we looked at different activation functions which are available for training a neural network. So this was what we covered last time. So today we'll move ahead and we will study one more learning rule that is known as a delta learning rule. Okay. So let us try to understand what the delta learning rule is. So the perceptron learning rule is, as we all know, is a binary neuron learning rule. So the initial perceptron model which was proposed was that of a binary neuron. So by a binary neuron, I mean that the activation function that is used for computing the output is either a bipolar or a unipolar binary function, binary activation function, the step function. Okay. So the problem with this particular type of learning is that it is not really able to solve non-linearly separable problems. And what do we understand by non-linearly separable problems? Problems which cannot be solved, or the patterns cannot be classified into two classes by means of a straight line. Okay, so there is some curve which has to be drawn so that it is able to classify it, right? So, so if these are some patterns, something like that. So this is one class, zeros is one class, this x is one another class. Okay, so you need to draw this kind of a curve, okay, which will classify these two patterns. Straight line will not do the job. So for um, a perceptron learning, it is not possible because only linearly separable patterns are solved, because the equation, it's in fact, it is a straight line, right? The sum of, how do we write the equation? It is wixi, right? Summation, some weighted sum of inputs that we have. If that is greater than or equal to 0 or less than or equal to 0, that is what we do, right? We write the equation of a straight line. That is a perceptron. So such, it is not able to solve uh, patterns or problems which are non-linearly separable in nature. So there was some initial solution to such problems, and the initial solution to such problems was to create a network which had multiple layers of perceptrons. Because a single perceptron cannot actually solve this kind of a problem. Maybe if you have layers of a layered network, so you can, one layer will draw one line, the other layer will draw another line, and then finally you'll be able to classify into those two classes. Okay, so the initial solution to solve such problems was to use multi-layered perceptrons. Okay, so multi-layered perceptron network is one which has some intermediate hidden layers. So we have already seen this kind of an architecture when we were discussing the very basics of neural networks in the introductory lecture of this particular unit. Okay, so you have the input layer, you have the hidden layers, one or more hidden layers, and finally the output layer, and each of these was a perceptron. Okay, so again, in this kind of an architecture was proposed, but again, still, this, it was found that this particular architecture itself is not sufficient to solve such problems because of the kind of activation function that is used in a perceptron. Okay, so the problem is that what happens is, for the first layer, that is a hidden layer. The input comes from the actual inputs of the problem. And for the second layer, that is the output layer, the inputs are the outputs of the first layer, right? So basically, I mean, let us call this as this input layer as layer 0. Okay, these are the actual inputs which are given to the network. So the network actually starts from here. Although in literature, sometimes this is called as layer 1, the input layer. Let me call this layer 0, and this is layer 1, and then you have a number of layers. Now, for simplicity, just assume there is one hidden layer, and this is layer 2 is the output layer, right? So for the first hidden layer, the input is coming from the actual inputs of the problem directly. Okay, and for the second layer, in this case, it is the output layer. The inputs are the outputs of the first layer. So whatever is the output of this neuron, this neuron, this neuron, these outputs actually become inputs for the output layer, right? So what is the problem with this? The problem with this is that the activation function which the perceptron uses is a hard limiting activation function, which just thresholds the net value to some value, either 1 or 0, right? It removes the information which is needed to train the network. Because of this, what it is doing is it is effectively, it is just masking of the output. Okay, it is masking of the inputs from the output layer. So whatever is going into the network as part of layer 0, what is happening is it is not going as it is. I mean, the net value is not uh, giving you a good estimate, because what is happening is the kind of activation that is applied at each layer is a thresholding activation. So that information is lost in some sense. And because that information is lost, okay, what happens is effective training cannot take place. So the solution to this problem was found by introducing activation functions which were nonlinear in nature. Okay, so that is when these continuous activation functions come into picture, like these sigmoid functions. Okay, so Widrow and Hoff actually they introduce a new type of a learning called as the delta learning rule, which makes use of nonlinear activation functions for training multi-layered perceptron networks. So these perceptron, the architecture remains the same, okay, but the kind of activation functions which are applied are sigmoidal in nature, or they are non-linear in nature. Okay, most of them sigmoidal. We have seen so many activation functions in the last lecture, and these are differentiable activation functions. So there are two characteristics. One, it is nonlinear, and the second is it is differentiable. The activation function should be nonlinear, it should be differentiable, so that effectively you are giving some useful information to the intermediate layers, and it is not shielded from the output layer. So it is passed on to the output layer. Now, uh, since we are using these nonlinear activation functions, the rule has changed, because each learning rule, what is the role of each learning rule? The role of each learning rule actually is to update the weights, right? They are different. They are different in the sense that the weight update occurs, right? So these learning rules, whatever we have seen so far, simple learning rules, Hebbian was very simple. It is exactly equal to the net value. Now, perceptron was again thresholding. Now, this rule, delta learning rule, since it is using these nonlinear activation functions, make use of some other weight update equation. So we will look at that model first, and then we'll derive the weight update equation for this. Okay. So delta learning, it is supervised, similar to perceptron. It is supervised. You require the label. It uses continuous activation functions, and the learning signal for this rule, it is called as delta, because the name comes from the learning rule. Okay, and it is defined as di minus, so look at the function, di minus f of w transpose x times f dash w transpose x, f dash of, so this f dash is nothing but the derivative. Okay, This is the learning signal. So what was the learning signal in case of perceptron? It was simply di minus oi, right? Di minus oi. In case of the delta learning, what happens is it has changed to di minus, what is this f of w transpose x? It is oi only, because f is the activation function. And this value that you see here, what is it? It is net, right? So this, in fact, this term is nothing but o. So di minus oi multiplied by f dash of w transpose x. So now you take the derivative of this activation function. Okay. So this term is net. So what you're doing is basically you're just computing the derivative here in this rule. So now the structure, if you want to view it diagrammatically, the neuron that we saw earlier, whatever neurons we were drawing, just for representation purpose, a binary neuron is a circle and a continuous neuron is a triangle. This is just a representation purpose, but nowadays no one is using a triangle. Everyone will, I mean, neuron is no longer now binary in nature. Neuron is continuous in nature. Okay. Although at the last layer you might threshold it for getting the class of the pattern, but all the neurons are continuous in nature, so the symbol has come out to be a circle only, but this is the original way of representing it. The triangle represents continuous neuron. Okay, so you get the, for this neuron you have the inputs, you get the output as usual, which is applying the activation function. This time it is nonlinear activation function over net. Then it is d minus o. So d minus o times, so this is d minus o times, it has to be multiplication. So d minus o times f dash of net. Okay, that is r, learning signal r. So r is d minus o times f dash of net. So c r x is your weight update equation for delta w. Okay, so this is how it looks like. So let us now derive this equation. So how do we get this equation for r? Okay. So now this particular rule actually can be derived from the condition of least squared error between O and D. Okay. So what we need to do is, this is the error, squared error, the equation for squared error, that is D minus O the whole square. Okay. So when now what is this half? Half is just used for normalizing it towards the end. So we will see this. So if we want to represent this O in terms of the activation function and the weight, so it will be f of w transpose x. Okay, so half of d minus f of w transpose x the whole square. So E is this. This is the error. Okay. Now what we need to do is we need to actually minimize this error. We need to minimize this error. So for that, for minimizing the error, you need to actually take the derivative of E with respect to weights, because the weights are the one which is adaptive. What is adaptive in this entire equation is the weights. You need to change the weights. So you are going to take the derivative of this error with respect to the weights. So when you take the derivative with respect to the weights, this term that you have got, okay, what is the derivative of that term? So it is half into 2 times, right, d minus o, that is f of this one. So that is half, the derivative of this, what is it? So half into 2 times d minus o, this is o, right, this is o, times derivative of this term. Okay, and whatever it is, w transpose x, and multiply it with x. Okay, so since we are considering I, so for that particular I, the x vector will be multiplied, because this W, you're taking the differentiation with respect to W. Okay. So, and one more thing is a minus sign will come outside because that is minus of f, d minus o. So you are taking derivative of that. So it is minus, this is minus of, right? So you get this term. So this 2 gets cancelled out and you get minus of d minus o f dash w transpose x times x. Okay. So this is the error gradient vector which we have obtained by taking the partial derivatives. And then if you talk about the individual components of this vector, then we can represent it by, in terms of partial derivatives, as dou e by dou wij, is everything is with respect to each individual inputs that are there. So xj for all xj. So whatever inputs are coming into the neuron for all these inputs, you can define this kind of a equation. Okay. Now this is the gradient of this error that we have defined. We have considered this kind of an error, that is the squared error. Now what we are doing is, since we have to minimize this error, so the weight changes that we need to do should be in the negative gradient direction. So I hope you know the gradient descent rule. So according to that, so the weight changes have to be in the negative gradient direction. Um, so delta W is in fact minus eta times this error. Okay, this error you need to minimize, and that is delta W, right? So minus eta times delta E, del E. That del E minus the eta that you have is nothing but the learning constant. It's a positive constant. It is a learning constant. Okay, and then when you substitute this del E in this equation, that minus and minus get cancelled out. So this you are substituting, right? This you are going to substitute here. So this minus and minus get cancelled. So you are left with eta times d minus o f dash of this particular net, f dash of net times x. Okay. So this is the weight update. This delta W that we see, this equation actually is the weight update for delta learning rule. So if you're talking about single weight adjustment, it will be with respect to all inputs which are connected to that neuron. So the weights of each individual input which is connected to the neuron. You will talk in terms of this. X is a vector. This capital X is a vector, right? So the individual x's you will write for each of these weights. Each of these weights which are connecting to the neuron, you are going to update it, right, with this equation. So this is the weight update rule for delta learning. So C is nothing but eta. It's eta is the step that you're taking in the opposite direction of the gradient, okay, in order to minimize the error. So small steps you're taking, right? Gradient descent. You're taking in the opposite direction of the gradient so that the error is minimized, so that you reach the global minimum. So that is the gradient descent. Okay. We will revisit this rule later on also, because this rule is extended for different loss functions. So far we saw this, the error function that we are considering is squared error. So similarly, you can extend it to other loss functions as well. Okay. So when we look at those kind of functions, loss functions, other loss functions, when we study deep learning in particular, we will revisit this again. Okay. So this is delta learning rule. Initial weights can be any random values. So your network, you can initialize with any random weights. And this rule is also known as a continuous perceptron learning rule, because it was introduced to remove the drawbacks of the continuous of the binary perceptron model. Okay, so it's a continuous perceptron learning rule. So depending on whether the activation function is bipolar continuous or unipolar continuous, and further assuming that lambda is 1, what we can do is f dash net can be expressed in terms of the output. directly. Instead of finding the derivative f dash net of the activation function, what we can do is we can express this derivative in terms of the output. Okay, so there are some equations which you can directly use. So if your activation function is bipolar continuous, then in that case f dash net is equal to half of 1 minus o square. Okay, half of 1 minus o square. So let us prove this first. So f of net, for bipolar continuous activation function is 2 upon 1 plus e raised to minus lambda net minus 1, right? So assuming lambda is 1, because more often than not we use lambda is equal to 1, so we get this, right? 2 upon 1 plus e raised to minus net minus 1. Now LHS is f dash net. So what we will do is we will prove that LHS is equal to RHS. So we will get an expression which is equivalent, which is making the LHS and RHS equivalent. So we'll reduce it to an expression such that LHS equals to RHS. Okay. So f dash net actually will be obtained by taking the derivative of this function f of net. Okay. So you, with respect to net, so d by d net of this activation function that we have. Okay, so let us solve it further and get an expression for it. So how will we compute the derivative of this expression? Look at the expression. The derivative of constant is 0. So the second part, so there are two parts to this expression. The derivative of this is 0, right? It's a constant. We now need to take the derivative, find the derivative of this term. 2 upon 1 plus e raised to minus net, right? So which rule you will apply? You can apply the u by v rule for derivatives. What is the u by v rule? What is the rule? Right? U dv by dx. If assuming a differentiating with respect to x divided by v square. Correct? So we will use this rule and we will find the derivative of that term, 2 upon 1 plus e raised to minus net. Okay. So that f by using that, okay, uv rule, u by v rule, f dash net. What is f dash net equal to? 2 is a constant. I'm just taking it outside. Okay, 2 into e raised to minus net, right? That derivative of this. So what I will do is I'm applying u by v. So v du. Okay, so this is u and this is v. So but this u in this case is a constant. So du by d net is 0. Okay, so the first term is 0. Okay, in the numerator, minus u dv by dx, right? That is this term multiplied by the derivative of this term. What is the derivative of this term? First is a constant. Okay, so it's 0. E raised to minus net. What is the derivative of e raised to minus net?
Minus e raised to minus.
Minus e raised to minus. Okay, and then v divided by v square. So 1 plus e raised to minus net, the whole square. Okay, this you're multiplying with 2. So the end result of this is nothing but 2 times, this is minus into minus plus, okay, e raised to minus net upon 1 plus e raised to minus net, the whole square. This is what you get, right? This is what you're getting. This is the LHS. Similarly, we'll try to get the RHS into this form. We'll try to get the RHS in this form, expressed in this form, so that we can prove it. So RHS is half 1 minus O square, which is nothing but, you substitute that O in this equation. Substitute the O expression for O in this equation. So half 1 minus 2 upon 1 plus e raised to minus net minus 1 the whole square. Okay. So what you need to do is we need to solve this equation and simplify it further so that we get it equal to the LHS. Okay. So again, here what I'll do is, let us simplify this term. So this is half 1 minus, this I'm just reshuffling this. So I mean, this is 2 minus 1 minus e raised to minus net, right, upon 1 plus e raised to minus net. This is the whole square. Then what we can do is half 1 plus e raised to minus net, the whole square, minus, this is 1 minus e raised to minus. Now there are different ways of solving it. You can simplify it in your own way. And then, okay, if I open these brackets up, a plus b the whole square, a minus b the whole square, right? So if I open the brackets up, what will I get? 1 plus 2 times e raised to minus net plus e raised to minus net, the whole square, minus 1. This is minus into minus is plus, 2 times e raised to minus net, e raised to minus net. Minus into plus is minus, minus net the whole square, right? So this, the terms, some terms will get cancelled out here, upon 1 plus e raised to minus net, the whole square. So this term 1 and minus 1 gets cancelled out. This remains, this 4 becomes 4 times e raised to minus net. These two terms get cancelled out. And so since this is 4, so this 2 will cancel out with one of the 2's, right? So you are left with this expression. That is, what is the expression? It is the same as the left hand side. That is nothing but 2 e raised to minus net upon 1 plus, yes, right? The same expression. So hence it is proved that when you use a bipolar continuous activation function, you can directly use this. So this will be helpful actually in solving the problems which are based on this particular learning rule. Similarly, if we are going to use the unipolar continuous activation function, then the output is O into 1 minus O. So can you prove this as an exercise? Yes. F dash net. What is F? I'm just writing the F of net for you. So what is O? O is f of net. In this case, it is unipolar continuous. It is 1 upon 1 plus e raised to minus net. Right? Unipolar sigmoid function. So using this, you will be able to prove, I mean, just substitute in the right hand side and get the derivative of this. Derivative of this is very similar to the previous one, must more simplified. Okay. So when you see, you will get the derivative of this term to be equal to the right hand side. You prove this because this proof could be asked in the exam. Sometimes this could be asked, these proofs could be asked in the exam. Okay. You'll be able to do it, right?
Yes, sir.
So let us solve one example on delta learning rule. Now, whenever we have a problem on delta learning rule, what is the problem is that since it is continuous activation function, that is a problem. Second thing is derivative. I mean, it is complicated, the equation. It will not be as fast as perceptron learning rule. Okay. But the method remains the same. I mean, the steps that you need to follow is the same, only the weight update will change from rule to rule, right? So x1, x2, x3 are the patterns. These are the desired outputs. Okay. Given these initial weights and the learning constant, C is given to be 0.1 and lambda is 1. That is fine. So we are assuming lambda is equal to 1 only every time. You need to calculate the final weights. You need to make use of the bipolar continuous activation function. Okay. So let us solve this. I'll share my screen again. Yeah. So whatever was given in the problem, that I've put in the form of a table, right? X1, X2, X3, three patterns, three steps. Okay. Simply have to follow this table. So initial weights also have been put up. Okay. The first step is similarly C values and the weight update equation has been written for your ease of reference. And one more thing is the activation function that is mentioned is the bipolar continuous activation function. Okay. So if you remember, we had proved that bipolar continuous activation function is actually the tan h function translated. So it is tan h of and scaled. Okay. So tan h of net by 2. Tan h of net by 2 is the same as bipolar sigmoid of net. Do you recollect this? Last lecture we had proved this. Okay. So it becomes easy to calculate. On your calculator, it will be easy to calculate tan h rather than using bipolar sigmoid. Okay. So first of all, the first step is always compute weighted sum of inputs, right? That is net. So what is net? Just multiply these weights, these inputs with these weights and sum them up. That is the value of net. So can you tell me what is the value of net? Come on, you have to solve this problem for me today.
2.5.
2.5? Next, O is tan h net by 2. So net by 2, you just put as an argument to tan h and tell me what is the value. Come on, use your calculator. Are you getting it as 0.848?
Yes, ma'am. Yes.
I am also computing along with you. Use the calculator if you're on a PC, or otherwise, see, please be in a habit to make use of the calculator because it will take a while to solve problems. So you need practice. Delta W1. Okay. So this is 0.848. First of all, you need to compute f dash of net. Okay. What is f dash of net? Use the formula which we have just derived, half 1 minus O square. So substitute this 0.848 in that equation.
Point 1.14.
0.14. Correct. Okay. Now you have f dash net with you, and you know the weight update equation. What is it? C d minus O. It's mentioned. I have just put it for your reference here. So it is C d minus O f dash net x, right? So multiply. C is given to be 0.1. 0.1 times d minus O. D is minus 1. O is 0.848. Okay. So what are you getting? Into x, individual x values. So for delta W1, this small delta W1, you will multiply with x1. For delta W2, you will multiply the C in D minus O into F. So these three values, are you getting it? 0.1, D minus O, F dash multiplied by x1 will be delta W1. Okay, similarly for this, you will multiply all these with x2. Okay, so first you compute this C into D minus O into F dash net. What are you getting? That you note down. Keep on multiplying with the individual values. What are you doing? What is the answer? Delta W1. It takes a while to solve this. That is what I am telling you. You need practice. 0.1
2.9.
minus which one?
Point C is 1 na.
C is 0.1. C is 0.1. I have mentioned it here. C.
minus 0.025872.
minus 0.025
872.
872. I can put it as 9, 4 up to 4 decimals. 872, right? So 87 is nothing but 9. Okay. Similarly, this. Apart from Harsh, no one else is solving, right? Delta W. So that term you keep it with you. C into D minus O times F dash X. So it will be easy to just put in the values one by one. This one will be 0, right? Because X3 is 0.
0.0517. Second one.
0.00517.
5174.
Correct. And finally, delta W4. It's the same as this,
Plus.
the first one, na? Only it is
Yeah,
positive.
plus.
Okay. Now what is the next step? Compute the new weights. You got the change in weights. So W plus delta W you need to compute. So you will get these new weights. So sum up this row with this row, right? With this row. So it is 1 minus of minus, sorry, 1 minus that. So it is 0.974.
741.
This one will be negative minus
0.9483.
9483. This will be 0 and this will be
0.5259.
0.5259. Yeah. So using this, compute net value. What is the net value? Multiply the x's with the w's and sum them up.
Minus 1.9483.
Next.
Minus 0.96. No, 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 no.
Tan h of net by 2, huh? Net by 2.
Net by 2. Yeah,
Hmm.
yeah.
Minus 0.75, no?
Yes. So f dash net
0.21875. 22 exact.
similarly compute these. So you understand that this is complex solving it. So if you get a problem on delta learning rule, you have to be careful and you have to be fast enough with the calculations. Okay. So delta W values. First is this is 0 only because x1 is 0, right? So this is 0. So now just compute C into D minus O into F dash net. So D is minus 1, O is minus 0.75. So minus 1 plus 0.75. minus 0.25 into 0.1 minus 0.025 minus 0.025 into f dash net. What is delta W2? Is it minus 0.0082?
Yes, ma'am.
Okay. Delta W3?
0.0027.
0.0027. Delta W4?
Yes, ma'am.
Okay. So this last row I'll leave as an exercise to you. The final weights I'll give to you as the answer so that you can verify them. So weights are, you verify this, okay? The last row you see, you should get this answer. So this is the final weights, W4. Okay. So just complete this last row as an exercise. Okay. I'll give you one more problem for exercise. I'll put it up on the classroom. Please practice these problems. Unless and until you practice, you will not be able to solve them. Apart from 2 or 3 students, I'm not finding any students who answer my questions. So I'm assuming that you are not practicing the problems. Okay. So we'll stop here for today. In the next class, we will see more rules. Okay. And this rule, of course, delta learning rule is a very important rule because uh, we have talked about delta learning rule with respect to a single neuron, but the same has to be extended to a layer of neurons and then to a multi-layered perceptron network. So we have to see what is the final weight update equation for that. Layer by layer, how it changes because you need to derive that equation. So we will look at that as well. But first we will look at all the learning rules which were proposed. Okay. So in the coming lectures, we'll look at more such learning rules. Thank you for today.